Assalamu alaikum. Hello everyone. So today we are going to start chapter 4. So this is in continuation of chapter 3. We started with the piping network system. So the some topics we covered in chapter 3 and some we will be covering in chapter 4. So here we will see that how the system behaves and what is the system characteristic and what are the dependent and what are the independent parameters of the network system. So as we know that the modified Bernoulli's equation takes the form, and we discussed this in the previous lecture. And so these three terms, we call it the mechanical energy terms of the fluid. So this is at section 1. So if you considering the section 1 here and we're considering the section 2 here, so these are the pressure, kinetic and potential energy terms at section 1. So combine these three terms, we can call them as H1, and combined these three terms we can call them the H2. So here we have the summation of frictional losses and summation of minor losses. So this equation can take the form like this, and we know that from the continuity equation that the flow rate can be defined as velocity and the area of cross section. So this is the velocity that we can define, and if we replace the velocity here, then we can substitute here, and then we will get this form of equation. So if we see in this form of equation, so either we can put this equation in terms of velocity or we can put it in terms of flow rate. So this head difference, and we call it the total head, and the total head difference from section 1 to 2, it can be written in terms of the friction losses and in terms of minor losses, and which comes out to be basically in terms of the flow rate, diameter, length, friction factor, and the minor loss coefficients. So if we see that what is the flow variable here, the flow variable is the flow rate Q, and so here this H1 minus H2, which is delta H here, is a function of flow rate square. So this is a kind of a parabolic equation, and we call it the system equation. And when we plot this system equation, then we call it a system curve. So why we are taking that all these as constant? So the last time I discussed with you the friction factor curve, and we saw that after a certain Reynolds number, the friction factor, when it comes here, where let's say the high Reynolds number range, the friction factor becomes almost constant. So all these terms is constant for the system. The length is fixed, diameter is fixed, friction factor it becomes constant at high Reynolds number, and summation k are constants. So these all terms are constants. So basically all together can make one constant, and the only variable is the flow rate here. So if you change the flow rate, that will change the head loss, basically the total head loss from section 1 to section 2. So this equation we call it the system equation, and when you obtain the curve for different values of Q, then that will call a system curve. So that was the first topic, and the second topic in this chapter is the equivalent length. So the equivalent length, the concept of equivalent length is that when we describe the losses, we have two things here. We have the friction losses and we have the minor losses. The friction losses we describe in terms of the friction factor, length and diameter. However, the minor losses we describe in terms of the loss coefficient. So we are finding a way that how to basically describe the minor losses in terms of the length, so that the equation takes the same form like the form it is taking with the friction losses. So we want to find out the equivalence of these minor loss coefficients in terms of length and diameter. So if you see this equation, again this is modified Bernoulli's equation, and then this is the energy terms, and then the friction losses term. So if we keep the friction losses all together, let's say this is the friction loss and this is minor losses are all together, and then we can write in this form. So our objective here is that we want to represent this summation k in terms of the length and diameter. So if you find, so if you see that how can we represent this in terms of the length and diameter, then we have here that so we have here the friction losses and the minor losses. So this term, the summation k, is basically is equivalent to summation fl over k. So we can represent this in the form that L equivalent divided by D and multiplied by F. So here this term comes out to be equal to this. So this is our just representation and nothing else. The minor loss coefficients are the real ones, which is measured in the beginning and through the experiments, and the equivalent length is just the change of terminology. So the summation k from this equation can be set as equals to F multiplied by L equivalent and D. So this LE equivalent is unknown. The D is the same diameter which we are using in friction factor equation. The friction factor is also the same which we are using in friction losses, but the LE is different. So LE value depends upon this summation K, and this LE we call it the equivalent length of the fitting. Equivalent length of the fitting. So here it is summation K, and if it is not summation K, then it can be simply K equals to F and LE over D. So that will be the equivalent length for a single fitting, and here the summation K is the equivalent length for all the fitting together. So this table shows that if we know the loss coefficient K, and as we saw in the previous slide, that the K is equal to F LE over D, and from here if you want to find out that what is your LE over D, so that is equals to your K over F. So if you know that what is the K for any fitting, and if you know that what is the friction loss coefficient for the system, so we can represent that in terms of LE over D. So here we have to make certain approximation that the friction factor is not varying too much. So for some kind of fittings, like this is the 90-degree elbow, the loss coefficient was 1.4. So this can be written as LE over D would be 30 for that. And if it is for long radius, then the LE over D would be 20 for that. So for some fittings, like this is for a flange kind of fitting, and this is 45-degree threaded, and this is 45-degree long, and then similarly we have the T joints, T through and T branch and T. So basically just the change of terminology that and this is useful when we do some programming, that we have the less number of variables, so that the calculation of the programming can be faster. So now we have the two options, like when you, because this table providing you the LE over D for certain fittings, not all fittings, for certain fittings. So if you want to use this Bernoulli equation for your network, then you have an option that instead of using K, you can use instead of using this expression which is in terms of K, you can use this expression which is in terms of LE over D, and LE over D can be seen in the table. So these are the further values for LE over D corresponding to the loss coefficients. Okay, so now we will see that the series and parallel connections, how do they behave. So here we have the pipe, that this is, we are indicating it by 0. So this is a piece of pipe here, and then we have the two parallel pipe, the one is going here and the other one is going here. So these are the two parallel connections, and so here they are meeting and here they are meeting, and then we have another pipe here, and then this is another pipe here. So this is pipe number 3, pipe number 4, this is pipe number 1, and this is pipe number 2. So if we want to find out that what is the net head loss, because the head loss in this pipe is HF naught, in this pipe is HF1, in this pipe is HF2, in this pipe is HF3, in this pipe is HF3. So the net head loss from point 1 to 2, so the net head loss from 1 to 2, so equals to the head loss this plus any of these two. So when there are parallel connections, we consider only the head losses in one parallel line, any one of the parallel lines, and by the system balance, these head losses has to be the same. They cannot be different. So here, the minor losses we are not considering. That what is the minor loss here? So for the time being, let's ignore the minor losses. We are only talking about the frictional losses here. So the HF1 we are taking, or we can take HF2 and then plus HF3 and HF4. So the series connections, the head losses are summed up. So this is basically the summation HF for series. What about the head? What about the discharge? So the discharge coming here, there is a Q naught, and which is bifurcated into two, Q1 and Q2. So remember here that the discharge need not to be same. It is not necessarily same. It could be same. So because it is bifurcated, so the Q naught equals to Q1 plus Q2, and again it is joined together, making it Q3, so which is equal to Q3 and equal to Q4. So these kind of balances you need to know about the network. So the next topic in this is the graphical symbols. That we have certain graphical symbols, and the standard for the graphical symbols of the piping network is NCZ 32.2.3. So this is the standard number, and if you want to find out the details for the graphical symbols. So here we need to remember that the pipeline is indicated by a single line. So if your pipe is going long, then this is your single line. If this is the one piece of pipe, it is connected by another piece of pipe, and then you have to show the connection. So if it is 90-degree band, for example, then you have to show uh, the connection. Then what is your connection? So there should be one line, or there can be two lines, or there can be a circle here, or there can be, for example, this kind of connection. So we can have here for the 90-degree the threaded joint, and we can have the flat joint, we can have the ball and spigot joint, we can have welded and soldered joint. So the different symbols indicating the different joints. If there is only one line, then it is indicating that your joint is threaded. If it is two lines, then it is flange joint, and if it is ball and spigot kind of joint, then it is shown by a curve, and the welded joint is shown by cross, and soldered joint is shown by the small circle. So this is just a joint in the pipe, right? And then if it is an elbow, so you have to show the elbow, but with the proper signs, like this one line is indicating the threaded, the double line indicating the flange, and similarly this curve and cross and a small circle indicating the ball and spigot, welded and soldered respectively. So if this band is large radius, then you have to write here LR. So that is indicating that your band is large radius, and this is 45-degree, and this is again the 90-degree, but this is reducing band. So it is reducing the diameter. So this is from higher diameter to lower diameter, reducing band. So it is a band, but it is reducing. So this number is indicating that it is reducing, and this line is indicating that what kind of joint is. So this is flanged, and this is ball and spigot, and so on. And this is union of the two pipes. So different kind of, like, this is the one line, this is indicating as the threaded, and this is indicating as flanged, and this is indicating as welded and soldered, and so on. So this is available, these kind of graphical symbols are available for almost all kind of fittings. It's like if it is a 90-degree elbow, if it is a 45-degree elbow, if it is a reducing valve, or union, if it is a like elbow, because it's a three-dimensional. The before you saw the word was a parallel elbow, and it is like elbow facing up, elbow facing down, T joint, and the T facing up, T facing down, concentric reducer, and it is eccentric reducer, and now it is valves, like this is gate valve symbol, this is grove valve symbol, this is check valve symbol, this is safety valve symbol, and so on. So when you are making your network drawing as per scale and as per following the standards, then you have to make sure that if your network has threaded joint, then you have to use single line. If it is a flanged, then you have to use the double line, and if it is a welded, then you have to use cross, and if it is soldered, then you have to use this circuit. So this is about the graphical symbols. Thank you. So this is it for this video. Then we will do in the next video, inshallah. Thank you so much.